This video is about nucleophilic substitution. What nucleophilic substitution actually is, the cases that you'll use, the general mechanism, and a couple of examples using hydroxide and cyanide reactions. So first of all, what actually is nucleophilic substitution? So philic means to like, nucleo is a bit like nucleus, and substitution is obviously you're replacing something, subbing something in. So what we get from this is something that likes nuclei are replacing other atoms. So at A level, you'll usually use hydroxide ammonia cyanide reactions, and what it basically does is replaces the halogen in a halogenoalkane, which, if you don't know what halogenoalkane is just simply an alkane with some kind of halogen added on, so bromine or maybe chlorine or something like that, and you've just got your simple hydrogens there. So that's what a halogenoalkane is. If we look at the general mechanism, so I'm going to take chloroethane just to demonstrate the general mechanism, which the chloro could be any halogen. So this carbon is delta positive and this chlorine is delta negative. That's because chlorine is a lot more electronegative than carbon. So if you remember, that means the shared pair of electrons are slightly closer to the chlorine as it's more attracted, giving it a slightly negative charge. Now what you have is an atom, which I'm just going to call A, with a negative charge, and this gives it a lone pair. This lone pair, because it's negatively charged, is actually attracted to this slightly positively charged carbon, and chloride, Cl-, is a very good leaving group. So what actually happens is this lone pair can come in and attack this carbon and kick out this chlorine, leaving this product. So it's ethane, it's the atom ethane, and Cl-, which is, if this is in solution of, say, water or something like that, Cl- is fairly stable, because if you think about it, table salt, NaCl, when you add it to water, it dissociates into Na+ and Cl-, and they are fairly stable in solution. So Cl- is nice and stable in solution and shouldn't reattack in, depending what that atom is, of course, because if it's a good leaving group itself, it could reattack in. But the point that we're looking at here is a negative atom can come in, attack the delta positive carbon, and kick out the halogen. So if we look at an example, if we use hydroxide, a hydroxide mechanism, if you've forgotten what it is, hydroxide is OH-, so something like sodium hydroxide will dissociate in water to Na+ and OH-. So when you attack, if we take chloroethane again, I'm just going to write the formula slightly differently to save time, and actually I'm going to write that in a different way. CH3, CH2, and Cl. So we have a delta positive carbon here and a delta negative chlorine there again. You've got this OH- with a lone pair on the oxygen because the oxygen is negatively charged. This lone pair will come in and attack the delta positive carbon, just like in the general mechanism that we saw, and this bond will break to kick out the chlorine, forming the product of CH3. See, still got the two hydrogens on there, and then you've now got the OH group on there, so the alcohol has been formed, the Cl- being kicked out. Again, this is fairly stable in water because the ions are stable, and for reasons that you don't really need to know until university. So if we now look at the cyanide mechanism, so hydrogen cyanide which if you don't know, this cyanide group is C triple bond N, is really toxic to the extent it was used in chemical weapons in the past. So what scientists do, if they want to do a cyanide mechanism, instead of using this highly toxic, that will probably kill you compound, they'll use something like sodium cyanide. Sodium cyanide can, again, if you put it in a solvent such as water, all dissociate into Na plus and Cn minus, the negative charge on the chlorine, and that has a lone pair. So what you can do, you can take the halogenoalkane again. I'll just take the exact same one to demonstrate the point, or actually we'll use bromine this time as the halogen. So you've got this delta positive carbon, delta negative bromine, as bromine is more electronegative than carbon. Then you've got this C triple bond N with a negative charge and a lone pair. So once again, the lone pair is attracted towards the delta positive carbon, attacks delta positive carbon, and the delta negative bromine is kicked out to form CH3, C, H2, and then Cn, which again Cn is C triple bond N, plus the bromide anion. And there you have it. There are a couple of examples in the general mechanism for this type of this type of substitution. I hope this video helped. Please like, share and subscribe for more videos. Let me know if there's any topics you'd like me to cover that I haven't done already. Thank you.